We're tackling 1.2.4 today, and our learning target today deals with symmetry. So I want to make sure that we're okay with reflection symmetry. I want you to be able to do some translation. And then this is kind of our key piece for today, is we're going to talk about symmetry, but it's not just because we're interested in finding things that are symmetric. You guys learned how to do that probably back in elementary school. Okay, the reason we talk about symmetry is that symmetry is going to help us come up with some relationships about shapes. And the one that we're going to be talking about today is an isosceles triangle. So in geometry is all about finding relationships between things. Symmetry is what is going to allow us to look at some specific properties of isosceles triangles. Does anybody remember what an isosceles triangle is? What's special about an isosceles triangle? Do you guys remember? Yeah. Good. Two sides of the triangle, they're the same. And exactly two sides, right? I like that you said only two sides. Because if three sides were the same, it wouldn't be an isosceles triangle. What would that be instead? It would be an equilateral triangle. Okay. Let's go ahead and turn to our page here, which looks like this. So we're actually going to start by doing some rotations. And for this, you may need tracing paper. Once again, if you don't have tracing paper, go ahead and grab some. There's some in this little box over here. Come grab one right now. They're giving us a series of shapes, and they'd like us to do some rotations. They're telling us which direction to rotate and by how much. And the big question is, does it always make a difference whether a rotation is clockwise versus counterclockwise? Are there sometimes when that does matter or it doesn't matter? And then can you think of a situation where after rotating you end up with the exact same shape? So I'm just going to do the first one here, just to remind you how this works. The highlighted point is going to be our point of rotation. So we're just going to trace the shape. And then I'm going to hold my tracing paper down with the tip of my pencil at that point, and I'm going to do the rotation. They wanted us to rotate it 180 degrees. 180 degrees is half of a circle. So if this is the top of my picture, I'm drawing a little arrow up here for the top of my picture. After I rotate it 180 degrees, that should be pointing straight down instead. So holding it down there, rotating it around until we're 180 degrees. That gets me to there. And then I just need to draw my shape, and you can kind of sneak your pencil underneath your tracing paper to draw some of your points. So I'm going to give you about 5 minutes or so to finish the rest of those rotations, and we'll come back together. If you finish early, you're welcome to have a look at the next assignment. Go ahead and look ahead, but please don't start working on the next problem until we have a chance to talk about it as a class. We're going to move on to 82, so flip the page over, please. All right, so we talked a little bit about some notation with angles when we were going over our assignment. I want to make sure that you guys are comfortable with some other notation as well. This notation right here, when you see two letters with a bar over it like that, that means that you're going to graph 2 points and you're going to connect them with a line segment. Now, a line segment is different from a line. Have you guys heard that term before, line segment? What's the difference between a line segment and a line? A line, that's perfect. A line segment stops at the ends, where a line is always going to go in both directions forever and ever and ever. So they're asking us to graph segment AB. Could you please go ahead and graph the 2 points that they've asked for and connect them with a line segment? Make sure that you're labeling your vertices or those points with A and B. In a moment here, we're going to be doing a transformation on this, and we're going to draw something new. That new thing's not going to have an A and a B on it. What's it going to have instead? A prime and B prime. So our learning target one of our learning targets last week was knowing the notation for transformations, and that was that prime notation. So the instructions here tell us the rest of the story. We need to use our tracing paper to rotate that line segment 90 degrees counterclockwise about point O, which is the origin. Let's go ahead and draw that point. It's already got a 0 next to it, so we'll just leave that like that. So we're going to go 90 degrees counterclockwise. If you can do this without the tracing paper, that's fine. Personally, I'm going to stick with the tracing paper because I tend to make mistakes without it, especially with rotations. And when I'm doing rotations, I find it useful to draw a little arrow someplace that's going to help me figure out when to stop rotating. We want 90 degrees counterclockwise, so I want to turn this direction until this arrow is facing to the side. Bless you. Question? Yeah, pass is available. It's the red pass in the back of the room. So go ahead and grab that on your way out, please. Okay, folks, I'm going to modify the next piece of instructions to make this a little bit clearer. Can we go ahead and do the next part, but let's just focus on the A points for right now. So the next instructions say draw dash lines between point O and the other 4 points. So let's just do the A points. So go ahead and draw a dash line between point O and point A. Excuse me, guys. I'm asking you to stop the side conversations. Okay. Thank you. And let's draw another dash line between O and A prime. There is something special about those 2 dash lines that we just drew. There is a special relationship between those 2 dash lines that we just drew. Does anybody want to guess what that special relationship is? There might be more than one. You think the angle between those dash lines is special? What do you think it is? You said you think it's a 90-degree angle? How can we test that? Do we have anything that we know is a 90-degree angle? What about like the corner of this tracing paper? I'm pretty sure that's a right angle. If I hold that up there, does that match? Oh yeah, it matches perfectly. It is a right angle. That is a 90-degree angle. Do you guys know how to mark 90-degree angles? With the little box in the corner? Go ahead and mark those 2 lines, that angle with a 90-degree angle. And let's tie this back to what we did last Friday. What do we call 2 lines that intersect and form a 90-degree angle? What property do they have? It starts with a P. They are perpendicular. So we have found that line OA prime and line OA are perpendicular. So that's one of the things. So it has to do with the angles. And I'm going to write some notation and introduce this to you now. It's going to come up later. So I'm going to write what I just said. Line segment OA. And then there is a symbol for perpendicular so that you don't have to write out the word perpendicular. This happens a lot in math because mathematicians are lazy/efficient. It looks like this. This is the symbol for perpendicular. Looks like an upside down capital T. And then what's a perpendicular? I'd say that's perpendicular to line segment OA prime. I would like you to practice naming an angle. We talked about this during the assignment review today. Could I get you guys to name this 90-degree angle here? How do we name an angle? We put an angle symbol in front. And how many letters do we need to name an angle? 3 letters. And what's the important thing about the second letter? What's the second letter going to have to be for this angle right here? It's going to have to be O. It's going to have to be O. This point right here, the name of this point where the angle is, has to be the middle letter. So we can either put the O in the middle and do A prime at the ends, or A prime and A. It doesn't really matter. The other two doesn't matter what order you do them in. I'm going to go A, O, A prime. But I could do A prime, O, A. But O must be in the middle. If I put A in the middle, I would be talking about this angle instead. Are we okay with the naming conventions for angles? So that angle, I'm going to write how much it is. We put a little m in front if we're talking about how big it is. The measure of angle OA, AOA prime is equal to how many degrees? 90 degrees. There's something else that's special about these 2 dashed lines. You guys nailed it when you said it made a 90-degree angle between them, but there's something else that's special about them too. Anybody want to guess what the other thing is? Stop. It has to do with their lengths. How long this dashed line is and how long this dashed line is. What do you want to guess? Do you think the lengths, which one do you think's bigger? This one or this one? Or do you think they're the same? You think they're the same? Would it make sense if they were the same? If I took this A and rotated it around, it's kind of moving around the edge of a circle. Aren't all the points on a circle the same distance from the center? That's what a circle is. So we could say that the lengths are equal. When we name lengths, we write the 2 letters, but we don't put a line over it. So when I say OA without that line over it, that means that I'm talking about how long that thing is. If I were to get out a ruler and measure it, I could put equals 1.7 centimeters or something. I'm going to write that it's equal to OA prime. All right, this is a property of rotations. When you rotate a point, it doesn't matter which direction you rotate, bless you, it doesn't matter which direction you rotate or how far you rotate, it's always going to be the same distance away from your center of rotation afterwards as it was before. So if I were to do the same thing and measure how far it was from O to B, it should be the exact same distance as from O to B prime. Does that make sense? So when you rotate something, the distance from the center of rotation does not change. Also, the angle that ends up here ends up being the same as your angle of rotation. All right, so we're going to use that to fill out some values here. So if I tell you that if I measure this angle right here, and this ends up being 7, Guys, look up here for a second, because this is a little confusing the way that I've written this. So if I tell you that this is 70, that's what I'm telling you right here. It's asking us now, what's the angle from HO to H prime O? What do you suppose that angle, this red angle that I just drew here is? Anybody want to make a guess? You think it's going to be 80? 75? What is it? It's 70 also. So if this angle is 70, can you guys pay attention, please, and stop talking? Thanks. If that angle is 70, then when I make an angle through my H points, it's also going to be 70. What do you suppose would happen if I made an angle through my S points? It ends up being 70 also. So all of those connected points, if you connect a point to the center of rotation to its original point, you're always going to end up with the same angle. The next one says if FO is 3.5 centimeters, that means if I were to actually get out a piece or a ruler and measure this and it was 3.5 centimeters, I think that's, or sorry, 3.0 centimeters. I think that's way too short for 3 centimeters. Then how big is this piece over here? You think those are the same also? They are. This would also be 3.0. And that's always going to be true if you're matching up corresponding distances to the center of rotation. So if I were to measure OH, that's this line right here, and I were also to measure, if I were to measure OH as this one, and I were to measure also OH prime, those are going to be the same also. So if OH prime is 6.8, then OH would also be 6.8. If SO is 3.2, then S prime O is 3.2. All right, any questions there? You guys are doing awesome. We are going to skip over the next part for now. Actually, let me give you just one thing that I need you to know about translations. When we give a translation, we don't talk about a line of reflection. We don't talk about a center of rotation. For translations, we have to tell how we're moving. And on a grid, that basically means we need to give 2 pieces of information. So if I started here, if I pick 2 points, any 2 points, I'm going with B and B prime. So 2 corresponding points. I could count how far I'm moving to the left or right, and then how far I'm moving down, and that would describe that translation. So for this translation, I would say that we are going to the right by 1, 2, 3, 4, 5, 6, 7 spaces. And then we're going down by 1, 2, 3 spaces. So to the right by 7 and down 3. And all my points are going to do the same thing. If I took A and counted over 7 and down 3, I would end up at A prime. All right, I think we can skip over the rest of that. Let's finish up with 84 here. Okay, this one's about reflection. So what we're going to do is we're going to take this line AB. Guys, pay attention here. I want to speed this up so I can give you some time for your assignment. Could you take this line segment AB and reflect it over line C? Use your tracing paper if you need to. Actually, you probably do need to because we don't really have a grid this time. So I'm drawing my line of reflection. I'm drawing AB. And we're actually going to flip our tracing paper this time. B ended up in the same spot. Did we expect that to happen? Because what's special about B? It's on the line of reflection. Anything that's on the line of reflection is going to stay in the same spot when we do a reflection. So B stayed right where it is. A did not, so I need to label this A prime. I'm not going to bother labeling this B prime because it's the same as B. All right. And then they're asking us now to connect the points A and A prime. So connect that with a segment there, straight across here. What shape did we just make? Three-sided shape is called a triangle. Is there anything special about this triangle? It's symmetrical. We know it's symmetrical because we created it with a reflection. I like that. What else? You think it's an isosceles triangle? If it's isosceles, that means that two of the sides have to have the same length. Are you guys convinced that two of the sides do? How could we convince somebody that this side and this side have the exact same length? I'm sorry? If we put it on a graph, we would be able to count and they would have corresponding points. How else could we? Okay, so this is key. Guys, please don't miss this. We just reflected this segment to get this segment. And what's special about reflections and also translations and rotations? They stay the same length. Does anybody remember that vocab term for transformations that don't change the size or shape of something? Translation's one of them. Also rotations and reflections. But there's a special name for those. Starts with an R. This is from a while ago. This is from a couple lessons ago. Those are called rigid transformations. Do you remember that term? Rigid transformations are ones that don't change the shape or size of something. And we performed a rigid transformation, which means these two have to be the same length. All right. Here's how we mark things the same length in geometry. We're going to put a little tick mark through that side, and we're going to put a little tick mark through this side. Do you see any other lengths that would be the same in our triangle? Are you looking at this little piece and this little piece there? Yes, yes, I agree. We don't have a name for this point. We could put a dot here and call it D. If we called that D, then you would have been talking about which two segments? DA prime. You got it. You got it. Awesome. So DA and DA prime would be the same also. How do we know that? Again, because we kind of created it with a reflection. Now, if these are the same, I don't want to put a single tick mark here and here because that would be confusing. That would mean that this was the same as this. So how do you suppose we're going to mark these? We're going to do double tick marks. If I ended up with two other pieces that were the same length, I would do triple tick marks. Like if so if I drew this and this, those are the same, you're absolutely right. And I would put triple tick marks on that to indicate that those are the same. There is something else that's the same in this triangle, and it's true in all isosceles triangles. And I'm just going to give this one to you because we're going to talk about it at length later on. This angle here actually ends up being the same as this angle over here. For the same reason. We created the one angle by reflecting the other one, and reflection is a rigid transformation. Oh, man. Yeah, I know. Well, show me what you got. I know. Well, what are you doing with it? Oh, you're putting your card in there. Okay. Thank you. Thank you for verifying that for me. You look like you were being all sneaky. It's okay. All right. By the way, so this is how we mark that angles are the same. There are a couple other equal angles in here. If I wanted to say these two angles were the same, I'd put double arcs in there. We're going to see that notation come up a lot. But the main thing that I need you to know from this is what we figured out about isosceles triangles is that they not only have two equal sides, they will always also have two equal angles. So that's our first property of a shape that we've developed through transformations, and we're going to do a whole bunch of those. So we're going to start talking about like the diagonals of a rectangle are equal to each other. The angles, the interior angles of a rhombus are perpendicular to one another. All these little properties, and we're going to develop them. We're going to prove that they're true by showing them with reflections, rotations, and transformations. And that's it for today, guys. You did awesome. Going back to our learning targets. Do you feel like you're okay with reflection symmetry? Can you recognize that? Symmetry is going to be a big thing next class. Do you feel like if I told you to take a triangle and move it to the left by 10 and down by 3, you'd be able to carry out that transformation? Yes, okay. And do you understand that we can use different transformations to come up with properties of things like an isosceles triangle? If so, you were very successful today. We have 15 minutes remaining for our assignment today.